Okay. Good morning. Sorry, good afternoon, everyone. So I have two announcements. The first one is that the deadline for Lab 5 is today. Make sure that you submit your peer reviews as well as your project. The quiz, the last quiz, will be released. I want it to be released after the deadline, so probably it will be tomorrow morning or late tonight. And the topics for the quiz will be everything up to Monday's lecture. So, well, Monday's lecture will not be included, but today's lecture will be included in the quiz. So that's basically all I have in terms of announcements. So let's jump into the lecture. Okay, so where are we? So what we're talking about is file systems. We talked about three main elements: files, directories, and volumes. And now we want to start talking about implementation of file systems. So I think one piece that was missing from the previous lecture was that what we want basically from our file system is to, as an input, get a human readable name or a path, and then give us the storage blocks where that file blocks are stored. Now, to do this translation, the file system usually has an internal state or internal variable, and that would be first translating from the human readable name to a file number, and then from file number to one of the earliest implementations of directories was to just use a linked list to store the data inside the directory. So basically the idea is that you have elements that have name, a file number, and a pointer to the next element in our directory. Now, let's say we're looking into file 110, which is basically the SMZ, and suppose that in this directory I have two more directories, SE350 and ECE350, and another file which is foo.txt. So every file, at least in Unix systems, every directory uses this dot and double dot to point to itself with dot, and double dot to point to its parent directory, basically the home directory. And then after that, we can just store the SE350 with its file number and a pointer to the next directory. Now we leave some space here if we end up having more directories added. And at some point we start storing all the files inside. So first the directories and then the files. In this directory, we only have one file, foo.txt. So that would be the last element, and it would just point to the end of the file. Now, this was actually the original version of Linux ext2. This is how it was implemented, or very close to what it was. Now, this is very simple, and it works fine if you have the directories with limited number of elements inside them. If you have a directory which has tons of files or tons of folders inside, then this becomes tedious to search for every file. You have to go through your entire linked list. So the complexity of search in a linked list is O(n), so n being the elements, and every time you want to search, you have to do O(n) search in your linked list to find the file you want. And this becomes like a bottleneck if you have files and directories with a lot of elements in them. So how can we break this down to get better search, complexity and runtime? If you have taken any algorithm course, the first solution or the first upgrade from a linked list is tree, and that's basically what is happening here as well. So you have tree-based directory layouts, which is very close to what you have in modern file systems. So what I'm about to show you is actually very close to what you have in Linux XFS, in NTFS, in ZFS, and so on and so forth. So the idea is to use something like a B+ tree, and just the idea of tree makes the search easy. Now, B+ trees are used in many instances to make search even easier. So the idea is to hash the file that you're looking for to a number, and then look for that number in your B+ tree. Now, for those of you who are not familiar with the structure of B+ tree, so each node has stores indices. Now, if you're looking for, let's say, 30 as your search index, you start with this list. What does this 240 means? It means that anything less than 240, you can follow this pointer. Everything more than 240 and less than 510, you can follow this pointer. Everything more than 510 and less than 730, you can follow this. And anything more than 730 to 980, you can follow this link. Okay, so now we're looking for 30, so it's less than 240. We will follow this link. Now the child by itself also has these indices. Again, 32 is less than 58, so we will follow this pointer. Now here we come. I guess I made a mistake. If I'm not mistaken, I mean, yeah, I'm pretty much sure I'm messing something up here, but it feels like this this pointer you follow for anything between 510 and 730, because then at this point, if you follow this link, it means that anything, yeah. Oh, never mind. I was right. For some reason I thought we're looking for 32. We're actually looking for 30. So everything I've said so far is correct. So never mind. Anyway, so now we're here. 30 is more than 15. 30 is equal to 30. So we will just follow this link. And at the end, we'll have this all the elements here. Now we can just immediately find them here by following this link. We got the element here. So this is basically just putting all these elements in an array, but then each one of these elements have a pointer that is pointed to by the internal nodes of this tree. So what did we do? We basically broke the search complexity to log n. Instead of having to go through all n elements, now we go through log n elements to find the file that we're looking for. Now, this is how you would implement it in a file system. So very similar to, I mean, the structure is very similar to what we saw in the linked list, but now we want to implement our B+ tree here. So as before, we'll use the first entries for directories, right? And then the end elements for the yeah. So the tree root is at well-known offset within the file. And then we will just use fixed size internal and leaf nodes to store whatever comes after the root. And then each tree node includes pointers to where in the file that child is stored. So now we talked about two different ways of implementing. There are probably more. You can add complexities. You can add other data structures as you as it fits your purpose. Now let's move on to the next task that we have in the file system. Let's say now I have found my file number. Now I want to follow this file number to find the storage blocks that are associated with this file number. So this is now what we were going to do. So this is we're going to talk about the implementation and how this would happen. So there are still aspects that we have to be careful about and consider when we want to implement this task. So first of all, what what structure are we going to use to index our files, the blocks of our files. We'll see a bunch of different data structures that different file systems use to store each file's blocks. What is the granularity that we're going to use? The granularity that we're going to use is basically our block size. So the question is how big our block sizes are going to be and what implications they have. The other aspect that we have to consider is how do we find free blocks if, let's say, we want to create a file. How do we allocate? How do we know which blocks inside in the storage device are free? How do we handle locality? Especially like going back to the magnetic disks, locality was a big deal. Less so now with flash disks. But let's say you have a magnetic disk, so locality is very important because sequential reads have higher performance than random reads. So you want basically to, if you're writing a file, you want all the blocks for that file to be written in a sequential manner to sequential logical storage sectors, so that when you want to read them, you can get a better performance out of it. And lastly, reliability, which we'll talk about in the next lecture if we have time. Okay, let's start with the most basic implementation. Again, linked list. So let's say we have a file name and we want to find blocks in storage blocks associated with this file. So one of the first implementations that was introduced in 1977 and originally was used with floppy disks. I don't know how many of you have seen them. But this actually has survived. So it's even now, even today, fat file systems are being used, and we'll see why. So there's an underlying reason that these were very popular and they're still being used. So how does it work? The idea is for each storage block that you have, you will have an entry in a fat tree, in a fat table. So, I mean, it's kind of like redundant because fat is basically file allocation table, but I'm going to say fat table, which would mean file allocation table, but just bear with me. So we have a fat table, and for each storage block, we're going to have an entry in our fat table. Now, we get a file number, let's say file number 31. To index into our fat table. And then from there, we can just follow the pointers to see where our files are. So each one of these correspond to a storage block, and that's how we actually find our files. So let's say I want block 5 of file 31. So if I have a pointer to the beginning of file 31, I just go there and I just follow 5 pointers to get to the block that I need. So once I find the entry that I need, I know that this entry is corresponding to a storage block, and then I can just bring that data to my file or write to it, whatever you want to do after that with that file entry, with that block. So what are the properties of FAT? So first of all, the first entry to your file is basically the first block of your file. We need to have a free list because that's how we find that which blocks are free. But the way it works is that if you want to find free blocks, you have to just manually go through all the elements of your FAT and see which ones are empty. So with this file system, unfortunately, we don't have any extra data structure. We're just using the FAT table to see which blocks are empty and which blocks are used. Next, if you want to grow a file, if you want to add more blocks to your file, or if you want to create a new file, all you need to do is to find a free block and just point the end of your file. Sorry, the last entry. Let's say we're adding another block to a file. We just follow the linked list for that file to find the last entry. Once we find the last entry, we'll just expand it. Instead of this last entry pointing to end of the file, it will point to another entry in the FAT. And that basically means we have allocated an extra storage block because each entry in FAT corresponds to one entry in your storage or one storage block. The same if you want to create another file. So if you want to create another file, all you do is you basically start that file from somewhere, and then just that somewhere has to be a free block, and then you continue with that. You just add blocks by making a linked list. So where do we store FAT? Somewhere on the disk. That's the option we have. What happens when you format your disk? Well, what you do is you just zero all the blocks that you have in your FAT, and you zero all the blocks in your storage, and then you make all your FAT entries free. What happens when you do a quick format? I guess still you can do quick format. So with quick format, you really don't zero all your blocks. You just make all entries of your FAT free. So this is one of those instances where the storage doesn't need to know what's going on in the file system. So you leave whatever was stored intact. You just free your FAT table. The data is still stored, the old data, but there is no way to access that data because your FAT is basically formatted. So I mentioned that FAT actually survived and it is used even today. Like if you buy these SSD cards or if you have flash memory, usually these are FAT32 or other variants of FAT. The reason is that FAT is very, very simple. It's easy to find free blocks. It's time consuming, but it's easy. So all you're doing with FAT is just implementing linked list. It's easy to append a file. It's easy to delete a file. All of it is easy. We're not talking about like complexity, but easy to implement, easy to understand, easy to reason about. And that's why they survived. Okay, what are the disadvantages of fat? So the disadvantage comes from the element that we're using. Well, we're using linked list, and searching linked list, as we saw before with the directories, is basically time consuming, and the complexity is O(n). So let's say if you have a big file and you want to access the last blocks of your file, you want to read the last blocks of your file, you have to go through the entire entries of your file to find the last entries. And that's time consuming. The other thing that fat is bad at is poor locality. So if you go back to what I mentioned about how you can add another entry to your file, or how you can create a new file. So all you're doing is you find randomly one of the, I think there are two ways. So either you can always start from the first entry of your fat table, find a free entry and use it. Or let's say you have already found one, you scan from where you are through the end of your fat table to find another one. There are different ways to do this, but what ends up happening is that you're not really keeping files and blocks of a file together, because it's kind of like, in essence, you're randomly picking a free block and then allocating it to your file. And as a result of this, what was very common back years ago, when fat was actually used for file systems inside your actual PC, was that you would get really a slow performance out of your disk because of this, scattered blocks all over your disk. And there was this thing that people would do called defragmentation. And what it does is basically goes through your files and restructures the fat table and tries to find ways to make files basically have their blocks in one place. The thing about defragmentation is that it would take a lot of time, because what you're doing basically is moving data in your disk, and it could potentially, depending on how big your disk is and how fragmented your disk is, hours and hours to defragment your disk. But every once in a while, I remember myself who will do that to get better performance, and it would actually be noticeable. After you would do a defragmentation, for a while, your performance would be noticeably better, until you delete files and you write new files, and then you get fragmented again, and you would have to do defragmentation. There was no support for hard links, or for that matter, soft links. And there is a reason for this one, which is kind of important. So there is no file metadata stored per file. So if you go back to the slides, we're just talking about how you store the data blocks of your file. We don't talk about metadata because it doesn't actually exist in FAT file system. So the reason for this is because of the structure of fat data fat table. So we're accessing each file by associating each block of it to one fat table entry, and that takes away any opportunity we might have to store metadata for our file. Another consequence of using fat table was that we had limited volume and file sizes. So let's start with the volume. The maximum volume, the maximum number of entries you could have is 2 to 28. So the reason for this is that each fat entry is 32 bits. I think 6 bits you cannot use is reserved. So you only have 28 bits to use in your fat entry. So with 28, and then each fat entry is going to be a pointer to another fat entry. So how many fat entries can you possibly address? That would be 2 to 28. So now, depending on how big your blocks are in your storage, let's say if you have 4 kilobyte block sizes, then the maximum volume size is 2 to 28 times 4 kilobyte, and that would be 1 terabyte. So this is the most you can get as far as volumes goes. So the other limitation is that because you somehow have to encode your file, the size of your file, with these 32 bits, right? That's all you have to address your file, 32 bits for each entry. So somehow you have to encode the file size within these bits. So that dictates what is the maximum file size that you can get. And that would be 2 to 32 minus 1. So again, this basically means that the maximum size of each file is 4 gigabyte. Now, this was fine when FAT was introduced, and for a while, and even now, if you have an SSD, these numbers actually are fine. You rarely want to have a SSD that is more than 1 terabyte, or have files more than 4 gigabyte to store on your SSD. So, but this is what it is. So these are the limitations that you have. The other limitation that comes from lack of metadata is security and reliability support, lack of security and reliability features. So again, because you cannot store metadata, you cannot store file access rights, as simple as that. So you can't limit who can access what file. So everybody can access every file. And this is basically terrible. Okay. Now let's move on to other implementations for to find data blocks. Again, very similar to what we saw with directories. Where do we go from linked lists? We go to trees. So we're going to actually store our files using tree structure instead of linked list structure. So the first instance that we're going to look at is the Berkeley Unix fast file system, FFS. So this structure and this implementation is actually used in other file systems as well. It's not just FFS. So a very similar structure is used in ext2 and 3 in their newest or newer versions. The main concept in FFS is inode and iNumbers. So file number, we're going to use iNumber. So this I number, we'll use it to index into our inode array. So this inode array, if you want to have a similar a structure, think about the fat table. It's very similar to that. So we're going to store these inodes in an array, and then file number becomes an I number to index into our file, our inode array. So then once we find the inode inside this array, then using that inode, we can track all the blocks associated to a single file. Now, if you look at each inode, it will be a multi-level index, or basically a tree structure. The way it's implemented, I guess I mentioned that in the previous lecture, in Unix file systems, the system actually works great if you have small files. Now, this structure will actually work well with low and large files. It will, as we will see, it creates an asymmetric tree for us, and it addresses one of the biggest drawbacks of fat file systems, which was lack of support for metadata. Here we actually store metadata for our files as first-class citizens. And we also support free space. To search free space, we actually, this time, instead of going through all our fat entries, we do the simple thing, which is using a bitmap. For all the allocated blocks, we store 1, and then for all the non-allocated ones, we store 0. We'll see more about this. Okay, so here is how it looks. Now, this is my inode array, which stores my inodes. So if I have an I number, that would index into inode to correspond to a file. So let's say I have a number, inode, I number, I go to my inode array, and I get my inode. So this is an inode. Now, what do we store in our inode? The first thing we store in our inode is file metadata. So there is a fixed size, fixed size block at the beginning of each inode for file metadata. And there you can actually store users, groups, who is the user, who is the group that can access this file, and then what are the access patterns for users, groups, and others. So for each one of them, for the user, read, write, execute; for group, read, write, execute; for others, read, write, execute. So that would be 9 access control bits to store here. There's also set UID bit and set GID bit. And if the bit is set, then the group, whoever, like if the set ID bit is set to 1, then group, anybody other than the user can execute this file with the rights that the user of the file has. So the same with this get ID. So if this is set, then anybody other than the group, so the other ones, could also execute this file using the permissions that the group has. What comes after meta block is basically a bunch of pointers that create that tree structure for us. So we have 12 data pointers, direct pointers. And what that is that it's just a pointer to a data block. So if you have a file that is less than 48 kilobytes, so each one of these guys can point to a data block, which let's assume it's 4 kilobyte, and you have 12 of them. So you can easily address 48 kilobyte of data. So if your file is less than 48 kilobytes, that's all you need to do. You can just use these pointers to point to your data. And if you look at this, this actually covers all the way to here. So it covers all these little files that we might have, which basically means majority of our files, they only use these direct pointers in Inode. Now, occasionally we actually have bigger files that we have to store. That's where we are going to use these indirect pointers. So for indirect pointers, we have one indirect pointer, one double indirect pointer, and one triple indirect pointer. And that should actually be enough to cover everything all the way to 4 terabyte of data. Okay, so how does it work? Well, let me just get these off so that we can look at it. Okay, so with one indirect pointer, this pointer will point to another pointer, which then would point to other pointers. So if this indirect block is by itself 4 kilobyte, then here you can actually address 4 megabyte of data, I believe. Yeah, so with the first one, with the first indirect pointer, you can address 4 megabyte. Then the double indirect, which means that it's going to point to a pointer, which then will point to a bunch of other pointers, which then will point to data blocks. You can store all the way to 4 gigabyte. And then for the triple indirect pointer, you can go all the way to 4 terabyte, which means that you have 3 levels of indirection. So let's summarize what we saw. First, we have metadata, good news. We can now store access rights and other things that we might want, access time, permissions. We have 12 direct block pointers. That would mean 48 kilobyte we can cover with these pointers. We have one indirect block pointer. So the way it works is that let's say if each indirect block is 4 kilobytes, and let's say you need 4 blocks per pointer, that means that each indirect block has 2 to 10 pointers for direct blocks. So 2 to 10, and each one of these is 4 kilobyte. That would be 2 to 10 times 4 kilobyte, which gives you 4 megabyte. Now with the double indirect pointer, the same. So the first one has 2 to 10 indirect block pointers. And then each one of them has 2 to 10 direct block pointers. So in total, you get 2 to 20 direct block pointers. And each one of them is 4 kilobytes. So you just multiply these and you get 4 gigabyte. Now, at this point, you have to also consider all the previous ones that you have stored. So if you end up here, the maximum size that you can have just by using double indirect, and direct pointers is 4 gigabyte plus 4 megabyte plus 48 kilobyte. And then the triple one is basically 2 to 30, ends up supporting 2 to 30 direct blocks, so which would be 4 terabyte. But then you still have the lower levels. So 4 terabyte plus 4 gigabyte plus 4 megabyte plus 48 kilobyte. This actually gives us an asymmetric tree. It's a shallow tree if you have a small file, and it would be a skewed tree if you have large files. It would be a deep tree. You're going to have to use multiple indirections to store your big file. And if you have a sparse file, let's say here is an example. Let's say you create an empty file, then you write 1 byte at the beginning, then you seek to, let's say 4 gigabyte, and then you write a block. So in total, you only wrote 2 blocks, but because you seeked to, let's say 2 or 4 gigabyte into your file, from the operating system's point of view, the size of your file is more than 4 gigabyte, if that's what you did. So writing 1 byte at the beginning or 1 block at the beginning, then seeking for 4 gigabyte and then writing another block. So in total, you're about 4 gigabyte of size. But in reality, what the operating system, what the system stores in its storage is only those those blocks that you wrote, plus the inode stuff, all the pointers and indirect pointers. So the actual size of your file is less than what the file size is. So file size is 4 gigabyte or more, but the actual data, the actual storage that is being consumed to store your file is much less. It's just a bunch of kilobytes of data, which is something very good. So you're not wasting. You could think of this, if you were to do this with FAT, you would have to use all the intermediate FAT entries. They should all just point to the next one and point to the next one and point to the next one. That basically means that all those blocks cannot be allocated to anybody else, right? But here, I'm not even consuming any data block. So here is a bunch of examples. How many accesses do you need to access block number 5? And the answer is just 1, because it's within the 12 direct blocks, direct pointers. So you just go to the 5th one, and that takes you to the 5th block of your file. Now, what about 23? Here you need 2, because you're in the portion where you need 2 pointers, 1 to an indirect pointer and then 1 to your data. And if you need more than that, let's say 340, then you're in the realm of 3 accesses. So you basically have a double indirect block, which then would point you to an indirect block and then point you to the data block, and so on and so forth. Now, FFS had some optimizations for magnetic storage. Because magnetic storage has its own limitations, as we discussed, FFS decided to store data in a smart way to get much more performance out of it. So here are some of the things that they did in FFS to speed up the performance of magnetic storage. So in early FFS versions, they would store the inode array, and for that matter, the what is it called, the bitmap for the free blocks. All of them were stored in one place, usually in the outer cylinder of your magnetic disk. And this actually introduced a lot of inefficiencies, because for each file that you want to access, you first need to access its inode, which would be which would mean that the head should seek to the outer cylinder and outer track to read that inode. Then once you know where they are, now you have to seek again to where the file actually is. So, and that is time consuming. So because it just requires multiple seeks. Let's say if you have indirect accesses, that would mean even more seeks. So they fixed this. It had an easy fix. And the fix was, let's divide the inodes, the inode array, into groups. And by doing so, we can actually put inodes associated to each group next to its data. So they basically divided the disk into regions, and for each region, they stored the inode associated with files in that region next to that region, both inode and also the free storage. So this actually dramatically decreased the amount of seeking needed to find files and dramatically improved performance. In addition to all of that, it also helped with some notion of reliability, because if you have all your inodes and free blocks stored in one place, and then you get bad sector in that area of your disk, basically you lose the entire data structure that you have for your file system. But by dividing it and distributing it throughout the disk, even if one of them gets, one of them gets bad sectors or fails, the other one's still there. So you don't lose your entire file system data. In addition to that, they also added another optimization, which was reserving a fraction of a space. We actually talked about it a little bit. We talked about sector sparing and page sparing in flash disks, but very similar idea here. This is actually file system doing it. It's not the disk doing it. The ones that we talked about, sector sparing, is done by the drive, the storage drive. But here the file system actually does this. So the file system does not use, let's say, 10% of the capacity provided by the storage drive. And why is that helpful? Well, this is helpful if you get, let's say, fragmentation. You can use this space to allow, let's say your disk becomes really full, right? You can keep this space, leave it or allocate it to the super user, let's say the sudo of your system, and the sudoer would come and take care of the system cleanup and make some space. If you don't have that, then you can't even run the sudo utility apps. So that's one. I guess I started from the bottom. Yeah, so the other one is that, as we will see, the way files are being allocated. So I still haven't talked about this free space bitmap. I will talk about it, I think, in the coming slides. But as we will see, initially when your disk is empty, it will try its best to put files next where their inode is. So after you group them, you do your best to, like, if the inode is here, to put your file in this region associated to group 0. But at some point, you probably this group will be full, and it won't be having extra space for the files to come. At that point, it does a best effort. It tries to find some other group and put the data there, somewhere else. But then, if you could imagine, if all the groups become almost full, then you start actually scattering your files all over your disk, getting to the same sort of problem that we had with FAT. And that slows it down, right? You're not going to get sequential reads, and slows everything down, and it's just not good. So to avoid that, keeping this 10% unoccupied will help you, when you get to that point, to divide this 10% now to 5% and allocate that 5% and keep the other 5% again as preserved to deal with these scattered files. The other thing that you can do here is you can actually, when you reach to that point, you can just prevent every further writes, get your sudo a program that is in charge of cleaning up your disk activated, and now at least you have some preserved storage device, preserved storage capacity to allocate to that application that is going to clean up stuff, and then hopefully that could help speed up the performance and get your disk cleaned up. So this is actually a very important optimization to keep in mind if you end up anywhere designing a file system or doing something close to that. Now let's talk about this data block placement. So here as I mentioned, we're going to use a bitmap to allocate our files. So any block that is allocated, that is already allocated, will be set as used, and any block that is free is going to be set as unused. Now, when you write a file, you're going to use a first free heuristic, meaning that you're going to just go through this bitmap, very similar to, you can actually implement this in FAT as well. Go through the entire list until you find a free block, and then allocate that free block, and then again walk through your bitmap, find another free block and allocate it there, and so on and so forth. Now, if you have a small file, this will lead to scattered blocks. But if you have a big file, then going through this heuristic at the beginning, you may actually fill up some holes, but then you get to the free space because everybody is just using from the first entries of this bitmap. You hope that the last entries are mostly empty, and if you have a big file, it will just fill up some of the beginning ones, but then it will get some good chunk of it to be written in sequential blocks. Now this is good because in essence, for small files, you really don't care much about how they're stored because you only have few blocks and you're already gonna seek for the first one, so it's fine if you seek for the second one as well. But if you have a big file, then it actually is very important to minimize the number of seeks. And this first free heuristic actually helps us with that. Yep. And again, you can actually put this in the context of groups, right? You can now will have one bitmap per group if you have the magnetic disk. Okay. Let's have 2 minutes of break and then I'll continue. Okay. So let's analyze FFS. I think it's FFS. Yeah, it's where was it? Sorry. So it's actually good for both the small and large files, as we saw. We can store them both. With the heuristic that it uses, it actually provides some notion of locality if you have, if that's what you care about. It also has metadata, and it also provides locality for metadata because all of them are stored at the same in the same block. And usually defragmentation is not necessary. It still could help, but it's usually not necessary. Now, what are the downsides. It's kind of like inefficient if you have really small files, because the inode itself is kind of big compared to, let's say, if you have a file that only needs 1 byte or 2 bytes, because you're already allocating all those indirect, direct and indirect and double indirect and triple indirect pointers. So basically you already have allocated some overhead at the beginning to store inode for files, even if they're not using it. So it's kind of like inefficient. The other thing is that if you have contiguous files, so if, let's say, you're lucky, you're the first file in the system, and all your blocks are written sequentially, the structure doesn't exploit this. So from the point of view of inode, it doesn't really matter. So for each one of those blocks, you're gonna use a pointer anyways. So you're not gonna exploit the fact that you could potentially have most of your blocks written contiguously. We'll compare this with NTFS when we talk about NTFS, and this is one of the areas that is covered with NTFS. It also reserves 10 to 20% of the free space, which might not be of your interest if you want to use the entire capacity. So again, as I mentioned, this 10 to 20% is preserved to prevent fragmentation. But if you are willing to pay for fragmentation, you might not want to lose 10 or 20% of your capacity. So here is how it's actually implemented in a Unix system. So let's say you open a file. What it does is that it first consults the directory structure, which we talked about. Is kind of like a B+ tree. So from there, you get your inode. Using your inode, you go find your inode. And then using your inode, you will just find the blocks that you are interested in. Bunch of other things to note is that after you do this resolution and you get your inode, you kind of, not exactly your inode, but what is called in Unix systems a file descriptor is created for your file and is actually stored in your PCB. Okay, now let's move on to the next file system that we're going to talk about, and it's called New Technology File System. This is a proprietary file system developed by Microsoft, and I think initially was used. Not sure. I think with the DOS. I'm not sure. If I'm not mistaken, it was DOS, but I might be wrong. So they used it to, they developed this to provide some improvement to their FAT file system. And basically what it does is that it adds metadata, it adds security and reliability support to FAT. The building block of NTFS is something called extent. And what each extent is basically representing a region of your file that is stored contiguously on the storage device. So by this contiguous region, I mean virtual sectors or virtual pages. So any region of your file that is stored contiguously on the storage gets its own extent. So if your entire file is contiguous on the storage device, your entire file will be represented by one extent. If you have a bunch of regions, if you have divided your file for whatever reason, if the disk was fragmented and your file got divided into 4 regions, then you will have 4 extents. So a similar, I have to mention that similar concept actually exists in Linux ext4. Now, we're still going to use tree instead of linked list because it makes much more sense. And the tree is going to look a lot different than the tree we saw in FFS. So here in FFS, if you had a deep tree, it basically meant that you have a bigger file. In NTFS, that's not the case. Because as I mentioned, let's say you have a 1 terabyte file, a file as big as 1 terabyte. But if all that 1 terabyte is stored in a contiguous region, then you only allocate 1 extent to this file. So your file is actually very shallow, but it's big. So there is not much, there is no direct link between the size of your file and how deep your tree is in NTFS. What a deep tree mean in NTFS means a fragmented file. So as your file gets more fragmented, meaning that it will have its blocks allocated in different regions of the disk or the storage system, then you will have deeper trees, as we will see. Very similar to where we started with fat table, then inode array. Now here we will have a master file table, MFT, that will store the roots of the trees for us, for each file. Very similar to inode array, as I mentioned. And our directories are actually organized based on B plus tree structure. Now let's look at it. So this is our MFT. Let's say you have a very small file. If you have a very small file, you can store your small file in one entry of MFT. So let's look at all the entries in this entry. So we usually store some standard information about our files. This is, you can think of it as metadata for your file. So when it was created, when it was modified, who's the owner, what are the security specifications for this, what are the flags, is it read only, is it read write execute, what is it? So this would be the metadata. Then you would have your file name. And after that, you will store attributes for your file. So what does attribute mean? So you have actually 2 types of attribute. You have resident attributes and you have non-resident attributes. A resident attribute means that that attribute, whatever that is stored in your master file table entry. So all it has, everything about that attribute is stored locally in that entry. So if you have, let's say, if you have a very small file, 1 byte, 2 byte, let's say 8-byte file, you can use the content of your file as an attribute, and you can store it in this entry. So it becomes a resident attribute, and that attribute is actually your data file, the data associated to that file. Now let's say that it's not actually this small to fit in one MFT entry. Then you will have data that is non-resident. Now your data is still an attribute, but it's non-resident attribute. And as I mentioned, here you're going to be using data extents. So what that means is that you have a start. What is the beginning of this extent? And what is the length of this extent? Two attribute will tell you everything you need about this extent. And you might actually have a file that is divided into two extents or one extent. Doesn't really matter. So you can use this now to address your to keep pointers to your extents. Now you could now think of a very big file which is contiguously stored in your file system. So you might actually have a very big extent, but you can only use one entry here and then use one pointer to the extent for that file, and you would be fine. So it doesn't really matter how small or how large your file is, as long as you can have a small number of extents for that file, you can actually store your file like this. Now let's say that your file gets fragmented and you end up having a lot of extents. So at some point, this area here will be not enough to store pointers to all the extents that you have. So in those situations, you will create an attribute list. Right after your metadata, you will have an attribute list. So your file name by itself is an attribute. So this would point to all the attributes that you have. Now, you could allocate another entry in your MFT, make your attribute list to point to that entry or to point to the region of that entry that contains the files, the pointers to the extents that you have. So here is how things would look like if you have a file that is scattered in 5 different contiguous regions of a storage device. Things could get a little bit, things could escalate and become worse than this. So you might actually have a lot more extents so that even this one doesn't suffice. Then, as we will see in next slide, this attribute list could also become a non-resident attribute by itself. So let's look at that scenario. Yeah, so anyways, I've talked about these. Now, I just set the stage for when things get messy, but let's just as just putting in everything together, let's look at all the stages that your file could go through. Let's say at the beginning, you start with a very small file. Everything fits in one MFT record. Let's say you start writing to your file gets bigger and bigger, but fragmented. Then you have to turn that resident data to non-resident data and start storing pointers to the extents that you have. Then at some point you have a lot of extents. You will have to introduce an attribute list to point to multiple entries for data. And then here is what I set the stage for. Things could get really crazy if you have a lot of extents, so that this attribute list cannot contain all the pointers, let's say. It could happen. Then this attribute list becomes non-resident itself. So you would have an extent for your attribute list, or bunch of extents for your attribute list. So this would happen only if you have huge files that are really fragmented. At that point, again, your attribute list becomes non-resident. You will have to have extents to store attribute list. So some more details before I end this lecture. Yeah, maybe actually, let me stop here and then I'll continue. Yeah, I'm already out of time. Okay, so I'm going to end this lecture here. Thank you for everybody who attended. We'll continue. I don't have much slides left for file systems, so we'll finish up file systems on Monday, and Monday will be the last lecture. So whatever time I have, I'll probably will talk about reliability. I really wanted to talk about virtual machines, but unfortunately we didn't get an opportunity to do so. So I guess I promised at the beginning of the term that I will talk about virtual machines, but unfortunately time didn't let us do so. So that's a bummer. But anyway, so last lecture will be on Monday. We'll finish up file systems, and then we'll talk about reliability a little bit. So with that, thank you again, everyone who attended, and whoever is gonna watch these lectures online. Take care, be safe, and talk to you on Monday. Bye-bye.